Okay, we're continuing on here, chapter 17, equilibrium. We talked about equilibrium last time, and again, it really involves a certain type of reaction, and it is those reversible reactions. And again, you typically will see these arrows that head in both directions, and as we talked about, that indicates that it's a reversible reaction. And what that means is it has really two directions. It has a forward direction, which is going from reactants to products. And at some point, there'll be enough products that they will actually combine and they'll actually head back the other way. And that was sometimes referred to as the reverse direction when your products sort of recombine and form back your reactants that you started with. And this process will continue to sort of go until they reach, as we talked about, what's known as chemical equilibrium. And chemical equilibrium is this part or the process where the rate actually of the forward direction will exactly equal the rate of the reverse direction. So as we talked about last time, it doesn't necessarily mean that you have the same amount of everybody on each side of the arrows, but it does mean that the rate at which they are moving will equal each other. And what that essentially does when this happens and it reaches equilibrium is it sort of locks everybody into place in terms of their concentrations. So whatever their concentrations are, once they kind of reach equilibrium, they will be able to basically maintain their concentrations, and it really will not change. And we saw sort of a graphical sort of look at that. So if we have our sort of reactants up here, and at the beginning here, our products, and this is our reaction in terms of time here as it kind of continues on. What we'll see is the reaction will start to go, thank you, in the forward direction, which means we will start to use up some of our reactants. At the same time, we'll start making some of our products as it's being made. And eventually, what will happen is they'll start to level off, actually, both of them, and they'll start to sort of go straight and sort of maintain their concentrations. This is sort of the concentration of everybody. And really, at that point where they level off, that is where equilibrium is reached. And again, because the rate of the forward reaction and the reverse reaction basically are the same, as soon as you sort of lose a little bit of reactants, they kind of come back the other way. And again, it basically keeps everybody sort of concentrated the same. It will basically stay the same unless you do something to kind of mess it up. And we'll talk about that today, I think. But if you don't do anything, they will be able to maintain that. Remember that in an equilibrium reaction, it may look like the reaction's over and there's not a lot of activity sort of happening if you just kind of look at a beaker. But there is a lot of activity if you sort of super zoom in. There's a lot of reactants going to products, products going to reactants to sort of maintain what you may see in the beaker. And as we talked about last time, when you look at the beaker, it just may look like a red solution. Not much is going on, but there is a lot of sort of activity that's actually occurring within that beaker. There is a relationship when an equilibrium reaction that is known as the equilibrium constant, and that is capital K, and that's the equilibrium constant. And we basically calculate it based off of the balanced equation and the coefficients. And the way that we calculate the equilibrium constant is we take K is equal to basically the concentration of our products divided by the concentration of our reactants. And in this particular example here, it would be the concentration of C to the C. So whatever the coefficient becomes like the exponent, our D to the D divided by our A to the A and our B here to the B. So it's basically our products over reactants. It is constant as long as the temperature stays the same. So the temperature, as we talked about last time, is the only thing that can affect the value of K. But if you keep the temperature the same, it doesn't really matter if you start a reaction with all reactants, all products, a little bit of everybody. It will always come to the same ratio of products to reactants, and it will be a constant value at a constant temperature. And K is actually just a number. There are no units associated with the equilibrium constant. As I mentioned before, we actually saw K in the last chapter, and that is Kw. And Kw is an example of an equilibrium constant value for water, and that was our 1 times 10 to the minus 14. So that's an example of an equilibrium constant, which is that Kw that we used in that previous chapter. Now, what does K really tell you? Since it's just a number, it does give us some important information about what is going on in that reaction. So, for example, if I have a large value of K, and since K is basically calculated by taking products divided by reactants, the only way to get a large value of K would mean that on top here would need to be large, and on the bottom would need to be small. And that would tell you that when you reach equilibrium, you mainly have products. So if you have sort of a large value of K, it tells you when you do reach equilibrium, you're going to mainly expect products to be present. Opposite is true if you have sort of a small value of K. When you reach equilibrium, you will mainly have reactants. And that's the opposite here. In that case, you would actually have a small value on top and a larger value on the bottom. That's going to give you a smaller value for K. And that will tell you there. Now, a large value or a small value, as actually a large value of K is considered to be above the big number of 1, basically. So anything 1 and above is considered a large value of K. Anything kind of less than 1 is considered a small value K. There are definitely different ranges of that. You could have really, really large values of K, something times 10 to the 54 power. You could have really, really small values of K, like to like the minus 36 times 10 to the minus 36 sort of value. And it can be anywhere in between. So it can be kind of extremes as well. The other thing that we talked about is when we write the equilibrium constant expression, there's really only two things that get included. We include in these expressions anything that is aqueous or anything that is a gas. You include in the expression for the equilibrium constant. You do not include anything that is a solid or a liquid. So anything with a solid or a liquid that's excluded from the equilibrium expression. That is why when we look at this example of an equilibrium constant, if you look at the equation for water, when it breaks apart into H plus, that's aqueous, and OH minus, that is aqueous. But water here is a liquid. So when we write the expression for K, it's our products, which is the concentration of H plus times the concentration of OH minus divided by our reactants. But in this case, we don't include that because that is a liquid. So it's basically divided by 1. So that's why when we get to the Kw expression that we saw, that's why it only looks like that. It only has the products involved because water there is a liquid. The reason we don't include liquids or solids, as we'll talk a little bit about, I think, again here, is again, liquids maintain a pretty constant concentration. So their concentration doesn't change over a period of time. And solids pretty much are just kind of sitting there, not really reacting too much, are involved very much in the reaction. Any questions on that there? All right. All right, so if we look at this equation here, or this reaction, we want to, what is the equilibrium expression? So once again, we're going to take our products over our reactants. And in this particular case, that's aqueous and that is aqueous, which means it does get included. So we definitely would include both of those. So H plus times C2H3O2 minus. And remember as well, when we do the little concentration here, we're really talking about molarity in most cases, moles per liter. And that's going to be divided by our reactants, which also is aqueous. So we're good to go on that. And that is, again, our expression here would look like so. So it would be A. Now, in order to actually solve for the value of the equilibrium constant, you do need equilibrium concentrations. So you always got to make sure that you do need have equilibrium concentrations. And you would actually, if you had the equilibrium concentrations for each of these guys, you would just basically put it into the expression and get an actual number. So let's talk a little bit about how we would get there. So if we wanted to calculate the actual value of the equilibrium constant, and we are given the equilibrium concentrations here, we would start with our expressions. So we would go to our formula here, our reaction, and go, it is the products, which is NO2. So this is a gas which would be included. We do need to take into account the coefficient there. So this is going to be NO2, and we're going to square it because of the coefficient. This is going to be divided by our reactant, which also is a gas. So that is the concentration of N2O4. Now, since we do have the equilibrium concentrations of each of these, all we have to do is basically put it into our expression, and that would give us 0.06, and we're going to square it, divided by 0.055, and we'll pop it in there, 0.06 squared. Just make sure it's right down there, 0.055. And it looks like we do have the right answer, so that's good, 0.065. Once again here, this is the answer. There's no units associated with value. This also would be considered a small value of K. Again, it's less than 1. And you can make a prediction that when this reaction reaches equilibrium, because it's a small value, you have more reactants than you do products in this case. And that's sort of what that value will tell us. Question of my calculation there. So there's different types of equilibrium, and there are some that are known as homogeneous equilibrium. And homogeneous equilibrium is much like a homogeneous mixture, which is everything is the same throughout. So what that means is in a homogeneous equilibrium, everybody's in the same phase. So everybody here is in the gas phase in our first example, and in our second example, everybody is in the aqueous phase. So they are all in the same phase, which means they're homogeneous in terms of the equilibrium. We could also have heterogeneous equilibrium, which is also like a heterogeneous mixture. In a heterogeneous mixture, we see different sort of phases, if you will. And that's also what we see here. So again, we see some solids and we also see gases. Here we got some liquids and we also have some gases. So it is possible to have an equilibrium that plays in the same phase. It's also very possible to have an equilibrium where it plays in different phases as well. Now, as we talked about previously, the position of an equilibrium is not dependent on pure solids and liquids. And again, we do not include those. So again, that is why we do not include anything that's a solid or a liquid. Once again, its concentration of pure liquids stay pretty constant. And a solid, if you just kind of think about it, just kind of sitting there, if you will. So it's really can't participate much if it's just sitting there. The only way it can participate is if it dissolved, and at that point it would no longer be a solid; it would be aqueous, which would participate in the equilibrium. So those two things again aren't included. That leaves us, as we talked about, the aqueous things and gases that are included in the equilibrium. And if you think about aqueous things, those are usually ions in solutions. So they're floating around and they're moving around and they're participating very well in equilibrium. Or if you have gases, obviously by the nature of gases, they have a lot of energy, so they are flying around and they're participating a lot within the equilibrium. So if we had a reaction that's a heterogeneous one like this, where we have some solids and a gas, we would write the equilibrium expression by taking our products, which is our O2, and we would cube it. We would not include this because it's a solid, and we would not have any type of reactants because that is a solid as well. So this would be our equilibrium expression. And as we talked about before, if you do it for concentration, that is sometimes referred to as the Kc value, C being for concentration. Now, what happens if you had a heterogeneous equilibrium where you didn't have anything on the product side that would be included, but you did have something maybe on the reactant side that would be included? And let's just say, for example, you had something like this. 2A goes to B here. That's a solid or something like that. And in this case, if we were to write the equilibrium expression for this, it would be K is equal to, since our products would not be included in here, we would do 1 over our reactants. So since we're not going to include what's on the product side because it's a solid, we would just do 1 over our reactants, which would be A squared in this case. So rarely, but occasionally, you could come up with something or see a reaction where nothing on the product side is included, but something on the reactant side is. So you just do 1 over the reactants, and that would do it. And it's kind of similar here. We just do products, so basically over 1 here on this side. Any questions on that there? All right, so if we take a look at this here, we're going to do our equilibrium expression. So once again, we're going to go our product. So this is all okay to include because it's aqueous. So it's going to be our calcium ions concentration. This also is going to be okay because it's aqueous times our fluoride concentration. Once again, the coefficient here is a 2. So we do need to square it because of that. Now, when we come to our reactant side, we're not going to include it because, again, it's a solid. So this would end up being our expression here. And by the way, this has actually a special symbol known as the KSP, which is a special type of equilibrium. It's not a solubility product, and it's the equilibrium constant for things that are insoluble. So there's a lot of equilibrium constants that kind of represent different things. There are ones that represent acids. There's ones that represent bases. There's ones that represent complex ions. There's one that represents, like here, things to do with solubility as well. So there's a lot of different Ks. They're all really calculated the same. It's always products over reactants, but sometimes they just relate to different topics. So if a change is imposed in the system at equilibrium, it can screw up the equilibrium. And the next thing we're going to talk about is Le Chatelier's principle. And Le Chatelier's principle is this idea of you basically have a system that's at equilibrium. So you got this nice system, it's happy, it's at equilibrium. And then you do something to it, and it's sometimes referred to as you add some type of stress to it. And when you add a stress to a system that's at equilibrium, and again, what we mean, obviously, with equilibrium is what we've been talking about, that the rate of the forward direction equals the rate of the reverse direction. When you add some type of stress to it, it actually will screw up the equilibrium. So no longer will the rates be the same going back and forth. And what will happen though is when you do this, it will want to return to equilibrium. And the reaction itself is sort of self-correcting. It wants to return itself back to equilibrium. So there's kind of 3 options that will occur as a reaction responds to whatever you did to it. So whatever type of stress you added to it is going to respond. And the 3 ways that it can respond when you add a stress to a reaction equilibrium is it will shift to the right. And what that means is obviously the right-hand side of the equation is products. So we'll head towards the product side. It could shift to the left. And obviously on the left-hand side of the reaction, that's where we find reactants. And the third option is actually, even though you did something to it, you technically screwed up the equilibrium, there can be no change. So, what are these sort of stresses that you could do to a system at equilibrium? You could do something with concentration. So, you could either increase or decrease concentration. You could do something with pressure and volume if you're dealing with a gas. You could do something with temperature. And lastly, you could do something like add a catalyst, which, again, as we talked about earlier, is something that you add to a reaction, ultimately to speed up the chemical reaction. It is not a reactant nor a product, nor does it get used up. So we're going to go through each of these sort of steps here and explain sort of what happens when you add or do something to these things to a system at equilibrium. So let's start with the first one, which is concentration. So really, when we're dealing with concentration, there's really two things that you could do to it. You could either add more, and typically when we add more, it will shift away from the side we added it to. And the other thing that you could do is you can remove some concentration. And when you do that, it will shift towards the side you removed it from. So when we talk about sort of to the left, to the right, removing and adding, we are talking about basically the reaction. So when the reaction, as it's written, we have reactants, we have products. So when we talk about, again, shifting to the left, we're talking about shifting to the reactant side. We talk about shifting to the right, we're talking about shifting to the product side. If we add something that's a reactant, then we're adding something on the left-hand side of the arrow. If we add something on the right-hand side, which is a product, we're going to do that. So when we add, it goes away. So AA is a good way to remember that. Add away. When we remove, it goes towards it. So just to illustrate this here, obviously, to add something, it's a very simple sort of task. You basically could just go to the reagent shelf, grab a bottle, whatever you need to add, and you could add it. So, for example, if I wanted to add iron ions to a solution, I could grab a bottle like iron 3 nitrate and just dump it in. And when I do that, that's a source of iron ions and nitrate ions. So it's like adding more of that to it. Removing is a little bit more difficult, especially if you have obviously a solution like we have in most cases here, and you got ions basically floating around. You can't just reach in with your hand and like grab out ions or something like that to remove it. So the very common way that we can remove something from an equilibrium is we add something to the solution that will actually make a precipitate. So typically we'll add something that will precipitate out an ion. So, for example, if we had this beaker and this beaker had chloride ions floating around in it, and you added some silver nitrate to it, that's a source of silver and nitrate. The silver would come in and actually find the chloride ions, and they are based on solubility rules, would make silver chloride, which is a solid, and that will essentially take out from the solution the chloride ions. And that is a very common way that you can remove something from a solution, is to add something that's not part of the equilibrium, but that will react with something in the equilibrium to make a solid. And remember that in the equilibrium, we don't include solids, so they're not included. So that is, again, essentially like reaching in there, taking it out. The other thing that you could do is, especially if you have hydroxide in your equilibrium, or you have H plus in the equilibrium, you could add either, depending on what you have there, an acid or a base. And when you do that, if you add an acid or a base, depending on the situation. So, for example, if you have hydroxide in your equilibrium and you add an acid basically is H plus, and hydroxide's OH minus. So those two guys will come together actually to make water. And making water is a pure liquid. And once again, water would not be included in equilibrium. But what that would essentially do is take out the hydroxide in that reaction. So those are two very common ways you could kind of remove something from an equilibrium, either add something that makes a solid or add some acid or base when you have OH minus or H plus in there to make water, and that'll essentially remove it. So let's take a little closer look at concentration here. So just to illustrate it here, if we had, say, a system that's at equilibrium, and we'll just draw some award-winning stick figures here. And let's just say the guy on the left here is the reactants, and the one on the right is our products in this particular case. And this guy, they are at equilibrium here. And let's just say that we decided to add some more people to the right-hand side. When we add more people to the right-hand side here, what's going to happen is we're going to end up with something that looks like this when we pop another person on. And now we could clearly see we are no longer in equilibrium, right? We kind of have a lot more products than we do, say, reactants in this particular case. So to fix this to get back to equilibrium, we actually need to put more people on the left-hand side. So it's going to shift away from where we added and go towards the left-hand side. And what's again going to happen is now we're going to get back to equilibrium, and we'll be back into an equilibrium situation now. And we are back to our equilibrium. So we added to the right, it shifted away to the left, and we make more reactants in this case. The reason this is really happening is, as you can see here, we actually have a lot more products available. It's going to cause the reverse reaction basically to occur in this particular example. Now, let's say we had the opposite. We had a system that was at equilibrium to begin with. And let's say we want to remove our guy over here, which is on our product side, and that's our reactant side. So we're going to remove the one on the right. And if that happens, what's going to happen in this case is we're going to end up like this. Now, in this case, to fix the equilibrium, we actually need more people on this side. So it's actually going to shift towards the side we removed it from. And this will return it back to equilibrium now type of state. So what is happening in this case? What's actually happening in this case is when we remove products, we actually have a lot more reactants in this case. And that's going to cause the forward direction basically to occur and shift away from it or shift towards it and going to make more products. You could think about removing like you made a hole on that side. So it's got to go towards the hole to kind of fill the hole. And when you add, it needs to kind of go away. So those are good ways to remember it, AA. And if you remove something, it goes towards it to kind of fill the hole that you made on that side. Any questions on constant? So basically, if you add reactants, it should shift towards the product side. If you add a product, it should go to the reactant side. If you remove a reactant, it should come towards the reactant side. And if you remove a product, it should go towards the product side. The next sort of Le Chatelier's principle deals with pressure and volume. And those things usually involve gases. And if you remember, our friend Boyle's law says that as the pressure increases, the volume decreases, and vice versa. As the pressure decreases, the volume will increase. So in a gas sort of mixture, when you're dealing with either pressure or volume, they are sort of tied together. So if we see the pressure increase, that means the volume decreases. So what happens in this particular case is you end up with a very small volume. And because of the small volume, there's going to be more collisions, and that's going to cause the pressure to go up. So what we want to do is actually bring the pressure back down. So that's the cause, basically, increase amount of collisions, pressure starts to rise. We want to bring it back to its equilibrium pressure, which is going to bring it back down. So in a small volume, the only way to bring the pressure back down is it will shift to the side with the least number of gas molecules. And what that means is instead of all those gas molecules in there, we now have a little less gas molecules present, and that's going to bring the pressure back down. So with pressure and volume, a lot of times you want to look at the volume. Small volume means we need less gas molecules. How do I know which side has the least gas molecules? You actually have to count them. So anybody with a G, you just count up their coefficients and figure out, there's like one gas molecule on the left, two on the right, and then that will tell you which one is the least number of gas molecules. Now, opposite of that, if the pressure goes down, the volume goes up. So we end up with a big volume in this case. And the sort of effect that's happening is the pressure is starting to come down. So we want the pressure to come back up. So we kind of want to rise it back up. So once again, in a larger volume, we would shift to the side with more gas molecules. And again, by putting more gas molecules in here, that's going to cause more collisions, and that's going to bring our pressure back up. So because these are tied together, usually pressure and volume, the recommendation usually is just think about the volume part of it. So again, if you have a small volume, you need less gas molecules. If you have a larger volume, you need more gas molecules basically to fill it up. Any questions on that there? All right, so let's take a look at one here. Let's say we had this equilibrium here, 2A plus B goes to 5C. And they're all gases here. All right, so for each of them, will it shift to the left? Will it shift to the right? Or will there be no change, which is a possibility perhaps in some cases. All right, so let's see here. For each of these, if I add more C, if I remove B, if I decrease the pressure, if I add more B. So take a moment for each of those to decide which way the equilibrium should shift in this case. Left, right, or stay the same, basically no change. Okay, so let's take a look. We'll start with the first one. We're going to add more C. So we want to figure out, looking at the equation, where C is a product. And when we add, that means it goes away from the side. So since we're adding a product, it should actually shift away from it, and it should shift to the left in this case. The reason for that, again, is we have a lot more products at this point. That's going to cause the reverse reaction to occur, and it's going to shift to the left. When we remove B, B is a reactant, so we're kind of creating a hole over here on the reactant side. And when we remove something, it always goes towards the side we removed it from. So it would cause the equilibrium to shift to the left to fill that hole. The real reason why that happens is, in this case, when you remove a reactant, you now once again have more products. And because you have more products available, they're going to start to react, and the reverse reaction in this case is actually going to occur. If we decrease the pressure, we know that's related to the volume. That should account for an increase in the volume. So when we have a large volume, we need more gas molecules. So looking at this equation, this guy is a gas molecule, so that's two gas molecules there. That is one gas molecule there. All I'm doing is just adding the coefficients that for anything with a G. That gives us a grand total of three gas molecules there on the reactant side. This is a gas molecule. Obviously, the coefficient is 5, and that would give us 5 gas molecules on the product side. So since we need more gas molecules in this case, in this reaction, more gas molecules is on the right-hand side, so it would shift to the right. Now, that is dependent, obviously, on the reaction, so you have to kind of count and see which side has more or less. Lastly, we're going to add more B. So B is a reactant. So when we add, it will go away. It will shift to the right and go towards the product side. Again, in this case, when you add more B, you have more reactants, and more reactants are going to cause the forward direction to occur, which is why it goes to the right-hand side. Any questions on that there? All right. All right, the next sort of Le Chatelier's principle has to do with temperature. And temperature works the same as concentration, which means if we increase the temperature, it should shift away. And if we decrease the temperature, it should shift towards it. So what determines sort of what's away and what's towards it and what side temperature's on? It has to do with what type of reaction you're dealing with. So if you're dealing with an exothermic reaction, that means energy is released. And when we think about an exothermic reaction, we think of energy and heat as being a product, like it is being given off. So if you have an exothermic reaction, the energy or temperature spot, if you will, is on the product side. Now, if you have an endothermic reaction, it is opposite. If you have an endothermic reaction, energy is absorbed. So we think of heat and temperature or energy as a reactant in this case. So heat plus our reactants go to our products here. So it is considered a reactant in this case. And that is how we know sort of which side, if you want to think about the temperature sort of value is on. Is it on a reactant or is it a product, depending if it's exothermic or endothermic? How do you know if it's an exothermic or endothermic reaction? Well, they could just write energy or heat on one side or the other, and that would tell you that it's either endothermic or exothermic. But more commonly, we see something that we saw in chapter 10 early on, our delta H. So our delta H of our reaction, if it's negative, is a exothermic reaction, which means it would be this guy here. And if the delta H is a positive value, then it's an endothermic reaction, which basically is this sort of situation here. So I would say that probably is the most common way exothermic or endothermic is given to you. Usually in chemistry, they'll just give you the delta H for the reaction. And if it's a positive value, you know it's endothermic. And if it's a negative value, it's exothermic. So if you have an exothermic reaction and you increase the temperature, that would mean like adding more energy here, it would shift away from it. And if you have an exothermic reaction, you decrease the temperature, that'll be like removing the temperature and it would shift to the right, in that case, towards the energy. If you have an endothermic reaction, you increase the temperature, that's like adding more reactants, so it will shift to the right away from it. And if you have an endothermic reaction, you lower the temperature, put everybody on ice, that's like removing a reactant and it will go towards the reactant side. So temperature works exactly like concentration. Add away, remove, it goes towards it. The key there is just to determine exothermic or endothermic as to know sort of which way it's going to do. Lastly, here in terms of Le Chatelier's principle, a catalyst can be added. And as we've talked about before, again, it's not a reactant, it's not a product, and does not get used up. It is only there to make the reaction occur faster by lowering that activation energy. And in terms of equilibrium, it will have no change on the equilibrium. So that is a possible answer. So if you add a catalyst to an equilibrium, it will just get there quicker, but it will not cause a change to occur. That's one way you could get a no change. You could also add something like a noble gas. If you add something like a noble gas, that also could cause a no change as they are chemically inert. And the third way you could actually get kind of a no change is if you had, say, a reaction like this, like 2A goes to 2B, and it has something to do with pressure and volume. I have on this side two gas molecules, and on the right hand side, I have two gas molecules, and it's a tie on both sides of the arrow. So there is no side that has more gas molecules or less gas molecules. So in a situation like that, that also would be a no change situation that could occur if you have equal number of gas molecules on each side and you do something to the pressure or the volume. There is no more or less. Questions on that there? All right, so let's take a look at another one here. Let's go with 2A plus 3B goes to 4C. We'll go the delta H is negative 125 kilojoules. All right, so we want to know, will it shift to the left, to the right, or no change? All right, let's go with add more A, increase the pressure, decrease the temperature, add a catalyst, remove C, let's go with 6 here, increase the volume. All right, so take a moment for each of those. Which way should it shift, to the left, to the right, or should there be no change? Okay, so let's take a look. So in this case, we're going to add more A. So A is a reactant, and when we add, it goes away. So we add it to the left-hand side. It then should shift away from it to the right-hand side. Again, here, by adding more A, we actually have a lot more reactants, so that's going to increase the forward reaction in this case. We want to increase the pressure. That means that in terms of our volume, the volume will actually go down. So remember that in a small volume, we need less gas molecules. So over here, we have two gas molecules. We have three gas molecules. That's a total of five gas molecules on the left. This is four gas molecules. So we need less gas molecules. So in this case, it is going to shift to the right towards that side in this equation, which has less gas molecules. We're going to decrease the temperature. So temperature works the same way as concentration. So when we decrease it, it should go towards it. It depends if it's exothermic or endothermic. So here we have a delta H given to us. The number is not important, but the sign is really important. The sign tells us it is exothermic. And because of that, we consider heat and energy a product. So in this case, if we are going to remove some product, it should then shift towards the product side in this case to kind of fill that hole. So because this is an exothermic reaction, we're actually removing more products, and that's why we're going to shift in that case. And obviously, it would be opposite. If it was endothermic, it would be on the other side. In this case, we're going to add a catalyst, which again will actually have no change in this case because I will not cause it to shift one way or the other. It just gets you there quicker. We're going to remove C. So C is over here on our product side. So when we remove it, it's going to go towards it to fill the hole. So it's going to shift to the right. Lastly, here, we're going to increase the volume. When we increase the volume, the pressure will actually go down. But in this case, we have a bigger volume. So in a larger volume, we would need more gas molecules. We calculated earlier, 5 gas molecules on the left, 4 on the right. So in this case, it would actually shift to the left in this case. Any question on any of those there? All right, so as we talked about concentration, shift to the right, shift to the left. Again, when we add, it goes away, and when we remove, it goes towards it. Obviously, volume affects really our gas molecules. So think about volume, small volume, less gas molecules, larger volume, more gas molecules. And exothermic or endothermic, again, either he's going to be on the product side in an exothermic situation, reactions on an endothermic situation. All right, so if we take a look here, consider this reaction. How many of the following would lead to a shift in equilibrium towards the reactant side? So what we're looking to see is, will this cause the equilibrium to shift to the left? So let's take a look at the first one here. We're going to remove CO. So if we remove CO, which is over here, when we remove it, it should actually go towards it, and that would cause it to shift to the right. So that definitely is not going to cause it to shift to the left. If we add more O2, O2 is over here as a product. When we add, it goes away from that side, and it would cause the equilibrium to shift to the left. So that would do it. The removal of CO2. So CO2 is over here. When we remove something, it goes towards that side. So this will cause the shift to the left. So that would do it. And if we increase the pressure by decreasing the volume, again, small volume, less gas molecules is what's needed. On the left-hand side, we have 2 gas molecules. Here we have 2 gas molecules plus one more is 3 gas molecules. So it should shift to the left here. So 3 of them will cause the equilibrium to shift to the left. It is these 3 right here that will actually do that. Any questions on that there? Let's take a look at this one. One method for the production of hydrogen by this endothermic reaction. How many of these would decrease the amount of H2? So in order to decrease the amount of H2, H2 is on the product side, we would need the equilibrium to shift to the left because that will use up some of the H2 and bring its concentration down. Now, let's take a look at each of these here and see what would happen. If we add more water to this reaction, H2O does affect equilibrium in this form. It's not in the liquid form, it's actually in the gas form. So it will have an effect on the equilibrium. So when we add more of water, it's a reactant, it should shift away. So it would shift to the right. So that would not do it. The volume of the container is double, so we increase the volume. We need more gas molecules. And over here on this side, we have 2 gas molecules. And over here, we have 3 and 1, which is 4 gas molecules. So this would cause it to shift to the right because we need more. That's not going to do it. CH4 is removed. If we remove something which is on the left-hand side, it should go towards it, and it would cause the equilibrium to shift to the left. So that's going to do it. And the temperatures increased. Since this is an endothermic reaction, that means that heat and energy is a reactant. So if we increase the heat and energy, it should shift away, which would go to the right-hand side and not work. So only one of them will do it, and it is number three is the one that will actually cause the equilibrium to shift to the left and also cause the concentration of H2 to decrease. Any questions on those there? So as we were talking about earlier, the K value does tell us that if, when we reach equilibrium, what we would expect, we have again a large value of K, we should expect mainly products. We have a small value K, mainly reactants. Once again, one is that sort of number that's considered large. So a K value greater than one is typically considered a large value. And again, anything less than that is a small value. A very small K again will tell us we mainly have reactants present, as we talked about. We basically calculate by taking products divided by reactants. So again, in order to get a small value, you would need a larger number on the bottom and a smaller number up on top. And that would tell you they mainly have reactants at equilibrium. The again, we could calculate K by using equilibrium concentrations. If you do not have equilibrium concentrations, you have to first figure them out, and then you could calculate perhaps K. The unknown equilibrium concentrations can be calculated if we do know the value of K. So here, the equilibrium lies to the right, or the product side. We would expect a large value of K greater than 1. If it goes to the left, again, we would expect a smaller value of K in this case.